Hello, today I'll be presenting a new algorithm for computing correctly rounded dot products under the round-to-odd rounding mode. So the year is 2026 and matrix multiplication is all around us. Of course, we can't do matrix multiplication without accurate dot products. Now, if you're working with finite precision, a real dot product result may not be exactly representable in your available precision. So under finite precision floating point arithmetic, the best you can do is the correctly rounded result. So this will be the real dot product rounded to your target format with one instance of rounding using some rounding rule. Now, floating point dot products involve floating point additions and multiplications, both of which involve rounding and rounding errors, which can hinder the accuracy of your final result. So getting the correctly rounded dot product at the end is a non-trivial task. Fortunately, there exist algorithms called error-free transformations, or EFTs, that mitigate accuracy loss due to rounding en route to obtaining the final correctly rounded dot product. Unfortunately, many of these error-free transformations, as I will explain later on, require that you perform your operations under round to nearest. Now, there exist other rounding modes without round to nearest properties that have their own use cases. One such example is round to odd. So when you're rounding a real number to a floating point number, you have two scenarios that can occur. Either the number is exactly representable to begin with, or your number is going to be surrounded or neighbored by two floating point numbers. Now, floating point numbers are composed of exponents and significants. If a significant ends with a 0, it's even. If it ends with a 1 bit, it's odd. And two consecutive floating point numbers have interchanging parities. Now, round to odd tells you if a given number is not exactly representable, always round it to a neighboring floating point number with the odd significand. Now, round to odd has very useful properties. First of all, it's unbiased, meaning the rounding error can be either positive or negative. So across multiple operations, the rounding errors can cancel each other out. Secondly, round to odd is composable, meaning if you round to an intermediate precision using round to odd and round again to a target format, it will give you the same result as rounding once directly to the target format. So this means that if you have a correctly rounded round to odd result for a high precision format, you can reuse the result across multiple formats. And lastly, as you may have inferred from the previous slide, round to odd is very simple to implement in hardware and is a good fit for accelerators. So currently, no standards support round to odd, but it will be supported by the upcoming P3109 standard on floating point arithmetic for machine learning. And we can imagine a scenario where future accelerators that support round to odd, perhaps as the only rounding mode, exist. Now, as I mentioned earlier, correctly rounded dot product algorithms that exist do not work with round to odd. So the goal of this research is to develop such an algorithm that works all the while using floating point operations under this rounding mode. So I will come back to the topic of error-free transformations, and due to the constraints in time, I will skip over some details about multiplication. But at a higher level, error-free transformations are algorithms that allow you to compute the rounding error induced by a floating point operation. And in doing so, error-free transformations allow you to preserve full information about the real arithmetic result. And error-free transformations for multiplication and addition can be used for dot products. So because of time constraints, I will skip over details about error-free transformations for multiplication. But just know that error-free transformations for multiplication that work under round to odd exist. And through such algorithms, you can reduce the task of computing an accurate dot product to computing an accurate sum over a vector. So that brings us to error-free transformations for floating point addition. So fast2sum is an error-free transformation that takes two inputs and produces two outputs. One, the floating point sum, and two, the rounding error induced by said sum. Now, fast2sum guarantees that the two outputs are exactly equal to the two inputs under two conditions. First, the first operand needs to have a greater magnitude, and B, the rounding error itself must be a floating point number. Unfortunately, this is only guaranteed under round to nearest, so this guarantee will not hold under round to odd. Now let's assume that we're still using fast2sum under round to nearest. Round to nearest and fast2sum can give you some interesting properties. For example, it turns out that the sum of the intermediate outputs z and y is exactly equal to b. So if you think about a as an auxiliary parameter that you don't care about, performing a fast2sum using b gives you the higher order bits of B, all the while preserving the overall content of B through an exact residual. So this opens up error-free transformations for vector operations. One such example is extract vector. So extract vector at a higher level first computes a power of 2 sigma that is configured relative to the maximum magnitude in the input vector v, and performs fast2sum element-wise to split each element into 2 components. And through this method, it turns out that if the exponent of sigma is large enough, you can add up all the extracted pieces accurately under floating point summation, all the while preserving the exact contents of the residuals through the second vector, v2. So imagine you apply this recursively, since it gives you back a residual vector. You get a descending order of residual vectors and a corresponding descending order of extracted sums. And using this idea, there is an algorithm called AXSUM that allows you to compute correctly rounded sums at the end. Only problem, AXSUM requires you to perform extract vector, which assumes fast2sum is an EFT, and that is not guaranteed under round to odd. So we work backwards. Fast2sum is an EFT if we discover new conditions that makes fast2sum an EFT under round to odd. We develop a new version of extract vector, and that will give us a new correctly rounded summation algorithm that works for round to odd. So I told you earlier, fast2sum cannot guarantee that x plus y equals a plus b in its original form. But all the way back in 1974, it turns out that fast2sum is an EFT under round to odd as long as you have the additional condition that a has an odd significand. So using this property, we realize that sigma's exponent matters, but its significand doesn't. So if a power of 2 has an even significand, its successor will have an odd significand, but the same exponent. So we just simply set the sigma to be a successor of a power of 2, and then proceed with extract vector as originally intended. So with that small change, we have a new summation algorithm that works under round to odd. We combine it with error-free transformation multiplication to get a correctly rounded result at the end.
All right, thank you to the speaker. And we will take questions.
Great talk. So one thing I did not understand is why ML community would care about round to odd mode. So there are only 2 things ML community care about. One is precision, accuracy. Another is speed. So if I do vector addition or vector multiplication using round to odd mode, do I get better performance or better accuracy compared to nearest to round to mode?
I see. So if you think about your 2 axes that you care about as performance and accuracy, round to nearest will give you the best accuracy, slow performance. Round to 0 will give you good performance, bad accuracy. Round to odd is a good middle point that allows you to exploit both points.
Nice talk. So when you do a dot product, there are 2 ways to look at it. One is to compute all the products and do a summation. The other is to look at it as fuse, multiply, add steps, FMA steps. So which one are we talking? And does your method work for a chain of FMAs?
Yes. So the only difference is how much the error-free transformations for multiplication matters. So if you change the FMAs, that becomes less relevant, but you need to still account for addition errors.
Other questions?
Yeah. Can we extend this to like weirdo floating point formats, or is this just like for IEEE floats?
So it is contingent upon IEEE 754's encoding. So IEEE 754, the encoding's parity matches up the significant parity. So we need that property for this approach to work.
Any other questions? All right, let's thank our speaker again.